Okay, we did exponents a couple lessons ago, so now let's just take it a little further and talk about a law of exponents. Let's go ahead and look at this. It's the product rule for exponents. We're going to see if you can discover a pattern before I actually tell you what the product rule is. Okay, 3 to the 5th is 3 times 3 times 3 times 3 times 3. 1, 2, 3, 4, 5, right? I don't know if we necessarily need to multiply that. I'm checking to see if the book wanted us to actually do that. Nope, I can just leave it there. We're just reminding you what that means. We have 5 3's. Now on this one, this is 3 squared times 3 cubed. What on earth does that mean? Let's show it out. It means 3 times 3, which is this part, right? So I'm just going to put parenthesis around that, times 3 of them. Okay. Now, could I remove these parentheses? Are they doing anything? This is all multiplication, so the parentheses really don't affect the value of the answer. And how many 3's do we have? 1, 2, 3, 4, 5. So that equals 3 to the 5th. Interesting. We had 2 of them, and we had 3 of them. Together we have 5. Do you see a pattern? 2 plus 3? Huh. Okay, let's see if there's a pattern on this one. Okay, 3 times 3 to the 4th. Okay, so that's 3, and then let's do 3 to the 4th there. Okay, and what does that simplify to? 1, 2, 3, 4, 5. Oh, look at that. In this case, we had 1 and we had 4. And they added together to make a 5. 2 plus 3, 1 plus 4. Notice this, 2 and 3, and the exponent here is a 4. But when you don't see an exponent, there's an invisible one. Mathematicians do not like having to write 1 if they can avoid it, okay? So I'm going to show you what that 1 is there, we don't write it. So that's a 1. What's 1 plus 4? 5. So you might have discovered the product rule, okay? Make sure, though, you notice that all of these had the same base. This would not have worked if these were 2 numbers, like a 4, and these were 3's. We wouldn't have the same answer. The base has to be exactly the same. They all have to be the same number. So like on this one, see how these all have the same bases. So we're going to be able to do that trick. Okay, the answer to this, if we have 5 x's, then we have 7 more x's, then we have 2 x's. How many altogether do we have? 5 plus 7 plus 2, so 14. And I didn't need to write all those x's out because I know how to count and you do too. Okay, this one, the answer is going to be 5, and how many 5's are there now? We have 2 plus 3 plus 2, so 7. And this will work for everything. So what you're witnessing is the product rule for exponents. Remember, product means multiply. When you multiply the same base, you add their exponents. When you multiply the same base, you add their exponents. Here I'm multiplying the same base, so I'm going to add their exponents. Okay, same base, add the exponents. So 530. There we go. All right, nerdy language alert, product rule. And this is the technical definition for it in math. If m and n are real numbers, right here and here, meaning they're not, imaginary numbers. Don't even worry, we're only dealing with real numbers for a very long time. So yes, they are real numbers, and x cannot be equal to 0. If x equals 0, none of this really applies. We don't take 0 to a power, okay? So they're just stating the base, the foundation. Then they're saying that when you multiply the same base, you keep the same base and you added this exponent to this exponent, and that's what they look like. M and n are representing any number, okay? So let's try this here. Notice we have not all the same base. We have x, we have y, we have x, we have y. However, the x's can multiply together and add their exponents, so that's x to the 7. And the y's can multiply together and add their exponents. Okay. Let's try it again with this one. Now we have a x, x, 2 y's, and an m by itself. So I'm going to, remember I like to do alphabetical order. Even though the book probably puts the m on the end, I'm going to look ahead. No, they put the m in front. Good. Nope, they put the m on the end. Oh well. I'm going to say m to the 5th. It doesn't matter because the order is not going to change the value of the answer. And now I'm going to take the x's. I have 2 plus 3 plus 3. So I have 8. X to the 8. Okay. Yeah, I'm looking in my book and seeing that I made a mistake writing it. So mine doesn't match the book. So sorry, I'm distracted by that. Mine doesn't match the book. Okay. And then y, there are 3 and 2. We have 5. Okay. And that is it, simplified. So we can take something kind of large, make it a little shorter. Kind of large, made it a little shorter. Okay, this is just a little, I kind of mentioned up above. X to the 1, we don't write that, is the same as just a plain old x. We just don't put the 1. But it's there, you just can't see it. Mathematicians can get a little bit lazy. They don't want to have to write that. So let's simplify this, knowing that if it has no exponent that you see, it actually does have a 1. So if you want training wheels and you want to put a 1 on there, you can. So that means we have 1x and 3 x's. So we have x to the 4th. Here we have y to the 1 and y squared, so that together makes y cubed. And there is our answer for that one. All right, let's you try this. Count up your m's, your p's, and your x's. The book puts m first this time. All right, so I have m to the 3, 4, because it's not there, but it is 1, 3, 4, and 2, 6. Okay, p, should we do p next? The book does x next. I'm going to do p because it's next in the alphabetical order. A p and a p, so we have p to the 6th. And then x to the 1 plus 3. X to the 4th. Okay, m to the 6th, p to the 6th, x to the 4th. You'll see the book has m to the 6th, x to the 4th, p to the 6th, and we're both right. It's all right if you rearrange the order. All right, now we're going to take this mess and start adding with it. So some of you are not going to like me. Remember like terms? Here's a little note. Like terms have the same letter or letters, write this down, and exponents in order to be liked. So they are very picky and particular, okay? So we're going to look across here and we're going to look for like terms. This, and we have I'm going to just say it. You don't see it, but we have 1 x squared y p to the 5th. Then we have 2x y squared p to the 5th. 3 p to the 5th x squared y minus 7y squared x p to the 5th. Okay, can I find anybody that has the exact same letters and exponents with this guy? So I'm looking for an x squared and a p to the 5th and a y. All right, here's an x squared, a p to the 5th, and a y. All right, these two are same family, okay? They're like, hey, I see you over there. I have 1. How many do you have? I have 3. All right, together we make 4. And I'm going to say x squared y p to the 5th, okay? So now they're happy. And then This guy goes, well, that was sweet. They just got married. How about us? What about you over there? Do we match? So I have an xy squared p to the fifth. What do you have? Well, I have 1x, a y squared p to the fifth. Different order, but that's okay, right? Oh yeah, that's totally okay. We can go together. So I have 2 and you have -7. What do we make together? We make -5, right? And I'm going to get, again, put it in alpha, or x, y, and p. How about that? X, y squared p to the fifth. Now notice, no one's exponents changed. When they got together, the exponents do not change when you are adding and subtracting. See how we added? All that added was the 1 and the 3. All that they did over here was group up with how many they had, a +2 and a -7. Everybody else stays the same. Do not mess with the exponents when you are adding like terms. Do not change those exponents. You're going to hate that because you change exponents when you multiply. You do not change them when you add and subtract. Alright, that's going to bother some of you. Okay, this one's tricky because if you, at first glance, they all look the same. Alright, so what we could do is put them all in alphabetical order to see if we can find any like terms. I think that would be the best thing to do. Put it, or do x, y, and p. How about that? So if we do that, this is 2xy squared m cubed p. That way it's easier to see. We're just going to put all of the variables in the same order, okay? Then this turns into a 3, an x, a y squared, m cubed p. So notice we have a little bit, oh, those are, I guess those two are the same. Okay, now let's see here, -10, I was thinking those were going to be different, x, y squared, m cubed p, plus, and it's a 1, right? They don't show it, but it's a 1. And we're going to say x squared y m cubed p. So I like to put them in order so that it's easier to see where my like terms are when they give you something this nasty. Okay, so now I can tell those two have the exact same letters and exponents. Okay, so these are like terms. Those two will get to go together. And then this at first looked like the same as that, but actually I'm noticing this also is a like term with these three. This one is like the ugly stepchild, didn't make it. Do you know why? These had an x to the 1, this has x squared. This had a y to the 1, the others had x squared. So these three are alike, this one's different. So all that means is we put all these three together without changing their variables or exponents. So there's what the term is going to look like, and the coefficient is going to be 2 plus 3 minus 10, which is a -5. Okay, and then this gets to do nothing, so we're just going to add it, but they don't get to group up because they are slightly different. So they, like I said, very particular, will not go with anyone who's almost like them. They will stay apart. Okay. Example 7. Again, add like terms. Notice they change shift orders. The y is in front of the x here. We might be able to see this. Here's the x in front. Everybody's got the x in front except for this one. So that's really 3x squared y. Okay. So here's an x squared y. Here's an x squared y. X squared y squared. So that's not going to play. Here's an x squared y. X squared y squared. Okay. So I noticed that this and these three are the same. And these two are like terms. So let's go ahead and combine them. So 2 plus 3 is 5, minus 1 is 4x squared y. And we have a +1 and a -4, which is minus 3x squared y squared. And there's our answer. Okay, go ahead and try the practice. Do your very best. I know it's could be a little tricky. All right, and be very careful. And then come back and watch if you don't get it. And okay, here we are. This is simplify. We're not adding like terms. Down here we add like terms. So these two are a little bit easier. We just count how many we have of each, right? So I'm going to start with my x's. I have to the 1, to the 4th, to the 3rd. 1 plus 4 plus 3. So I have x to the 8th. And then I have 1 plus 5, y to the 6th. Okay. This one I have 3, 1, and 7. 3, 1, and 7, so I have x to the 11th. And then I have y to the 2 plus 5, 7. And then I have m times m, or m to the 1 times m to the 1, which is m squared, because 1 plus 1 is 2. Alright, now we're going to move on to adding like terms. So I'm going to look, I've got x squared y cubed, xy, x squared y cubed, and xy. Okay, so these two are like, and those two are like. So together that makes negative 6x squared y cubed. And then this is a positive 1 and a minus, so we're going to minus 4xy. And notice when I write them down here, I put a mathematical. Okay. This one, x to the 6y, x to the 6y, xy, xy to the 6. So do you notice they're trying to trick us here? So the only two like terms here were these two. The rest are all loners, right? So there's two of those. So we're going to say 2x to the 6th y's. This, no one else gets to play. Plus 3xy, so we just copy them down. And that's as simplified as we can get. We combine two of our terms.